Alright, so this is the question. In this case, the liquid level system shown in the figure 1, the system is isothermal. So in the isothermal, so that means the temperature will not going to affect. When it is isothermal, no reaction is occur. So this indicate that the energy balance and the component balance will not be used for this kind of question. In this case, it just mentioned consider liquid level. So this means level. So how to get the level? It is from the overall mass balance. The diameter of the tank 2.5, 2 inlet, 2 outlet. So this is the process description in the volumetric meter cube per hour. The outlet F3 and F4 are exiting using pump and the valve. The linear valve resistance with respect to exiting flow relation is given as F4 equal to H over R. So in this case, let's say we have 2 inlet, 2 outlet. The F3 as shown in the figure 1 has the pump and the valve is located on the stream 4 or F4. So here your friend asked the question C. However, it may not sense for me to jump straight to the C. Let's go for the A first. Derive first order transfer function in the derivation form for given liquid level system. So based on this, so the answer we start with the dm over dt. So in this case, liquid level. So liquid level, that means you need the overall mass balance. So do not confuse yourself with the derivation of energy or component. It's not required for this question. So the m dt, let's say this one is the m1 plus m2 to indicate 2 inlet flow rate minus the m.3 minus m.4. Where here we can say that the m is equal to density multiplied by volume. And then this contribute to the d rho v over dt equal to m1 is the f is the volumetric meter cube per hour. So it will be rho 1 f1 plus rho 2 f2 minus rho 3 f3 minus rho 4 f4. So we can expand the equation rho dv dt plus v d rho dt equal to rho 1 f1 plus rho 2 f2 minus rho 3 f3 minus rho 4 f4. So this is your expansion. We can assume the density equal to rho 1, rho 2, rho 3 and the rho 4. So based on this, the d rho over dt becomes 0, and then we can further simplify our equation based on the constant density assumption. That leave you the dv dt equal to f1 plus f2 minus f3 minus f4. Since the question relate one or require you to develop liquid level, so the relationship is V equal to A multiplied by the H, where H now is your level in the meter. So we substitute the equation dAh over dt equal to F1 plus F2 minus F3 minus F4. So based on the expansion, A dH dt plus H dA over dt equal to F1 plus F2 minus F3 minus F4, where the area, the cross-sectional area against time, in this case, will be equal to 0. So you have the A dH dt equal to F1 plus F2 minus F3 minus F4, where in this case F4 equal to H over R based on the given linear valve resistance relationship. So you can substitute the H over R, F1 plus F2 minus F3 minus H over R. So this equation considered as the dynamic state equation for your case. So in order to develop the derivation form, then we have the A dH dt equal to F1 plus F2 minus F3 minus H over R. So for indicating the equation under steady state condition, we put the bar. For the A area, you don't need to put the bar because it's a constant. The H, you need to put the bar, F1, F2. And then the H. And lastly, for the resistance, you don't need to put the bar. How about the F3? So, like I mentioned before, here the F3, if we take a look, F3, you have the pump over here. When the pump, the function of the pump is to continuously regulate the flow rate at the fixed flow rate normally. Flowing the flow rate at the fixed value. So when it is conducted under the fixed value, then you don't have the F3 bar. Because F3 become constant. So in this case, this is the thing. So here F3 you don't have any bar. Then this contribute to the following derivation form. So for the derivation form, it become the A dH prime over dt equal to F1 prime plus F2 prime minus H prime over R. So this is your derivation where the F1 prime equal to F1 minus F1 bar. F2 prime become F2 minus F2 bar, and lastly H prime equal to H minus H bar. So this is the answer for the question 2A, where the question asks you to derive first order transfer function. So it's not complete yet for the given liquid level. So now we have the derivation form, so we need to proceed with the Laplace transform. Laplace transform. Alright. So here, based on the Laplace, you will have the A S H prime S equal to F1 prime S plus F2 prime S minus H prime S over R. Alright. So here we have the H prime. So here, if we try to categorize it, you have the H prime output. F1 is your input and input 1. F2 is your input 2. So, and then lastly, the H prime is your output. So the output appear on the left and the right hand side of the equation. So you can do the factorization later on. In this case, it is important to classify the variable. Why? Because we want to know how many transfer function can be obtained. Either single transfer function or double transfer function. Since in this case, there are two inputs, input 1 and input 2. So this means maximum you will get two transfer function instead of one. So here the rearrangement is S H prime S plus H prime S over R equal to F1 prime S plus F2 prime S. So based on the factorization, we have the AS plus 1 over R equal to F1 prime S plus F2 prime S. Since we have two inputs, input 1 and input 2 and one output, so like I said before, there will be a two transfer function. So here one of the transfer function will become here AS plus 1 over R. F1 prime S. So this is the first and second one. F2 prime S. So there are two transfer functions, although we can say that both transfer function has the same term. Although you have the same term, in this case, it's better you separate it in order to avoid confusion. If you truly understand it, it's okay to factorize it, but I strongly recommend to separate it in order for you to avoid the confusion later on. So based on this, it require the first order transfer function, so you can have the R ARS plus 1 F1 prime S plus R ARS plus 1. So this is your first order transfer function for the given question. Any question?
Doctor?
Yeah.
Doctor, can we directly start from the A dH over dt equals to F1 plus F2 minus F3 minus F4?
Yes, you can do that.
Okay.
In this case, what I want, because here I start from the scratch, from the conservation of mass principle, the MDT. If you're already familiar with it, you can skip the step. You can start jump away to here, the AHDT, this one. No problem. If you're already familiar with it.
Okay, doctor, thank you.
Any other question? Okay, if not, then we continue for the B. So this is your B. Initially, the inlet flow rate of F1 is set at 3.5. So this is the F1 condition, F1 bar condition. Meanwhile, initial condition of outlet, F2, F3 are given 0.1, 2.1 respectively. Based on the level measurement, initial height is 0.5. Determine the value of process gain, K, and time constant, tau. So there are two. K, in this case, although you have a similar K, it's still okay. So based on this, we want to find the K and the tau. So since based on the given information, we have the R, AR, S plus 1. So our K, if we try to compare the first order based on the given question here, K over tau S plus 1. This is also K over tau S plus 1. Meaning that our K, if we try to compare it, K equal to R. And the tau equal to AR. So here the A is for the area, cross-sectional area. And the R is the valve resistance. So A is equal to pi this square over 4, where the D stands for the diameter. So for this question, the diameter is given 2.5 meter. So we substitute inside the equation. Pi multiply with the 2.5 square over 4. So what is the answer? Please calculate it for me. Again?
4.909.
4.909. Alright. Any objection?
No, doctor. Same.
Alright. Then, okay. So we have the 4.909. So we have the cross-sectional area value. Now we turn our attention into obtaining the resistance value. So here the resistance is not given. If we take a look on the statement, so we just give the R without the value, the expression only, meaning that you need to calculate the value of R, the resistance. How to calculate it? So in this case, we take a look on the information. Based on the B, they give you the information of initially inlet flow rate F1. So you have the F1 bar 3.5. Initial condition of the outlet F2 bar 0.8. F3 bar 2.1. And then initial height H bar 0.5. So if we take a look, all of it has the bar, indicate that you need to use the steady state condition. Steady state condition has been generated in this case where you have the A dH bar dt equal to F1, F2, F3, H over R. So based on that, A dH bar over dt equal to F1 bar plus F2 bar minus F3 minus H bar over R. Where, like I said before, the at t equal to 0, A dH dt, A dH bar dt automatically becomes 0. So you have the 0 equal to F1 3.5 plus 0.8 minus 2.1 minus 0.5 over R. So you have one equation, one unknown. So based on the degree of freedom, of course, you can solve it. So what is the value of the R?
Kosong poin 2273 3. 0.2273.
0.2273.
Doktor nak tanya,
Ya.
dekat situ dia bagi F3 bar kan, tapi bolehkah kita terus masuk dalam F3 tu?
F3 bar and the F3 is the same one because it's a pump.
So boleh tak? Okay, faham.
Any objection relating to the answer? So
No, doctor.
the R is 0.2273. So now we know that the K equal to 0.2273. and the tau is equal to AR. A is the 4.909 multiply with the 0.2273. And then we multiply. What the answer for the tau?
1.116.
1.11?
1.116.
116. Okay. So this is your answer for the K and the tau. Let's complete the question B. So we have the K and we have the tau. So the C. Okay, now we go back to your friend's question. So here, after 5 minutes, the inlet flow rate of F1 is increased based on step change from 3.5 to 5.4. Okay, and a unit step change has been used for inlet flow rate of F2. Determine the time needed for the liquid level to achieve height of 1 meter. Alright, we go back to this equation. First of all, let me copy. Alright, now I have this. So the next step is for me to substitute the value where the R is 0.2273. The AR is 1.116. S plus 1. F1 times S plus 0.2273. 1.116 S plus 1. F2 prime S. Okay. So based on this, the next step relate to the Laplace inversion. We convert the Laplace transform into the time domain form. So since this is the first order, so that means the inverse Laplace so we have the H prime T equal to K1 M1 1 minus exponent negative T over tau 1 plus K2 M2 1 minus exponent negative T over tau 2. Alright. So this is the inverse Laplace for the given transfer function. Since it is under first order, has a standard form of first order, then we can straight away take the inverse Laplace form. Why I put 2? Because you have two transfer function. So one each for the transfer function. So here the H prime in this case, they determine the time needed for the liquid level. The time needed for liquid level to achieve height of 1 meter. So we know that H prime equal to H minus H bar. So in this case, the new H is 1 meter. The original H, the H bar is equal to 0.5. So in this case, although it's not stated the H bar inside the C, but we can use the information in the question 1B. This is what your friend asked before. If the question mentioned the state or the value in the B, can we use it or not for the C or D? Yes, in this case, we can use the information. So here we use the H bar equal to 0.5. So the information H bar 0.5. So that means H prime is 0.5. So for this part, 0.5 equal to K1. So here we have the K1 0.2273. And then we have the M1. In this case, we have the M1 and then the M2. What is the difference? It's based on the input. Yeah. So where the M1 refer to the F1 prime and M2 refer to the F2 prime. So what is the magnitude for the M1? M1, based on this, F1 is increased based on step change from 3.5 to 5.4. So this means the magnitude 5.4 minus 3.5. And then 1 minus exponent negative t over tau 1. Tau 1 is 1.116. So we have that for the first. And then for the second one, plus K2, 0.2273. And then the magnitude for F2. In this case, a unit step change has been used for inlet flow rate of F2. So what is the magnitude? What is the magnitude of F2?
One.
Why it is 1?
Because during when we calculate the H prime S, the other side we got 1 over S, so we can use the 1, right?
That is not correct. That one is like the assumption.
Is it because the question said unit step?
And why it is become 1?
Because means one.
Alright. Okay, this is the thing that sometimes we need to be very careful when reading the instruction. So I think during your degree, you already took several in couple or English subject, English for academic, English for technical, English for professional, too many English, right? So let me remind you, in this case, the term highlight here, a unit. So when you have the a unit, then this represent the singular. If you remember, you have the singular and plural. Plural, you put s, unit, you have the s, more than one. If a unit, then it's referred to the singular, which is equivalent to 1. So this indicate that the magnitude M2 is equal to 1 based on the given information. A unit step change, a unit. So for this part, the M2 is equal to 1. So that is the answer why. Let's say in the question, it does not state a unit. It just mention you the units like this. Then because it's a plural, then you can assume as long as it's not 1 or 0. So you can assume m equal to 2, m equal to 5, and m equal to 10, for example, like that. So this is a thing that you need to be very careful. So here the question give you a unit. So a unit refer to the 1. So m2 equal to 1. Then the remaining 1 minus exponent negative t 6. Okay. So we have one single question. Now you have the t as the unknown. Then of course you can solve the t. So what is the answer?
1.586.
1.586 hour. Anybody else get the same answer, or you may get the wrong answer or different answers?
Same answer, sir.
Alright, if we have the same answer, then we can agree. So this is the answer for it. T equal to 1.586 hour. In the test or in the final exam, you don't include the unit hour. I also accept it. No problem with the unit. No problem. So as long as the value is correct, then I will accept it. So, yeah.
As in the question, it mentioned 5 minutes. So do we have to do anything with that time?
Again, I'm not clear with your question.
Because in the question, it mentioned after 5 minutes. So do we have to do anything with the 5 minutes?
Okay, in this case, no. So here, normally, when we have the first order, it's like this. First order response. So we have the response like this. Normally, in the first order response, we use the step change. So the step change has the following response. So let's say in this case, this is your F1, and then versus T. So F1 originally at 3.5, and then it will be changed to 5.5 at T equal to 5 minutes. So in this case, that means the response will start to change after 5 minutes. So this is your 5 minutes. So this is your response. Where this is the typical first order response. It will be steadily increase and reach the final value. So for this part, this is 0. What is the H bar? 0.5. 0.5, and then this is 1 meter. So in this case, the 5 minute will not taken into account. So here the response T in the expression start after the 5 minutes. So we start fresh. We begin at 0. So you don't need to do anything with the 5 minutes. But the picture or the visual for indicating 5 minutes is like this. So for this part, one more thing, this to reach 1 meter. So this is 5. Only here, in order to make sure it's correct, we just add 5 plus 1.58. Oh, sorry, this one is 5 minutes, right? So we convert into the hour, and then you can add with this hour. Then you get the new value here. That's all. That's the thing that you can do, but you don't include in the equation.
Yeah, understood, doctor. Thank you.
All right. And okay, I think in this case, the last one, you can do it by yourself because the question has been solved. Only here, step change used in C, what will happen to the liquid level if the valve resistance value used is double. So originally, R is equal to 0.2273. Now, R is equal to 2 times 0.2273, which is equivalent to the 4546. So in this case, if we take a look, so this is your equation. We have 0.2273. So it will affecting on your K and the tau. Let's say for example, we take this equation. Alright. So we know that based on our equation, K equal to R0 and the tau equal to AR. So originally the R here is the 0.2273. Now it has been changed to the 0.4546. And then the tau equal to AR. AR originally 1.116. And since the R has been multiplied, so we multiply it, become 1.116 multiplied by 2, you get 2.232. So what we can do is to substitute again inside our equation. So here, this one, and this one. So we put 0.4546, 2.232, 2.232. And then this one 0.4546. Alright, why I change the value? Because here I want to compare with the original R value. When R value original, R equal to 0.2273, the time needed 1.586, 1.586 to reach 1 meter. So when R is double, how the time is affecting. So that's why I use the same equation and replace the R value. So in this case, can you calculate the new T for me?
Zero point 0.763.
Okay, thank you very much for your response, 0.763. So this means if we try to compare original R equal to 0.2273. The time needed is 1.586 to reach 1 meter. When I double the R value, the time is shortened to 0.763 only to reach 1 meter. So what is the effect of doubling the R value?
Decreasing the time.
So when we decrease, the time has been decreased, then what happened to our total response?
Respond he much faster.
Yeah, then your level response become quicker or faster if you double the R value. Since here in this case, we can see the time has been decreased. When the time time has been decreased, then your response become quicker or faster. So this is the explanation. So we support with the value. The value that you calculate, you compare with the original value, then you come up with the conclusion. So this is the answer for the given test yourself question.
Doctor,
Yeah.
for the when R is 0.4546, I get the T is 1.064.
Okay, we have a different answer here. You get 1.064.
1.064.
Okay. Anybody else get the a different answer for the
Yes,
T?
I got the same answer just now. Or 1.064.
1.064. Okay.
Yeah.
All right. One more response. Do you get 1.064?
Yeah, I get the
Yeah.
same.
Okay, thank you very much. All right, it's okay for the wrong answer. Keep trying. You already done the good work calculating the answer. Make sure you calculate it correctly next time. So here, sorry for that. So this is not our answer. So 1.064. 1.064 hour. Okay. So still in this case, what we can see, the time still decrease from 1.5 to 1.06. Still we can come up with the conclusion. The response, the level response become quicker or faster to reach 1 meter of height.
Okay, doktor, dah dapat. Sorry, salah.
It's okay, it's okay. We learn from mistake. No need to say sorry. As long you are learn something, then it's good. Any further question relating to this set of past test question?
Doctor, I want to ask again, because the question asks for what will happen to the liquid level. So our conclusion, so we should write like when the resistance increase, the level of the liquid system will reach the desired point faster. Is it right like that?
Yeah. In the shorter time, it will reach the 1 meter at the shorter time.
Okay, understand. Thank you, Doctor.
All right. So I open to any question. Okay, if there is no further question, then we take a break. And after 5 minutes, we continue with some discussion relating to the test. So we take a break for now. Okay, welcome back. So we enter the second period of our class. So I open to any question that you may have related to the process control and dynamic study. Yeah.
Doctor, can we discuss the exercise you gave on 6th April, the part C and D?
Part 6 April, which one? 6 April, which one? Is it the first question, right?
Yes, sir.
Okay, okay, all right. Okay, as requested, so let me share the first part of the question. Okay, this one, right? So
Yes.
based on the previous class, we already complete the calculate the response of the product composition at 5 minutes. So at 5 minutes, then we have the following answer, where the x is equal to 0.2815. So in this case, sketch the dynamic response of the product composition before and after the changes. All right. So in this case, we know that here in this one is just require you to have the dynamic response product composition before and after the changes. So that's mean okay. So in this case, we have the X bar. So normally the S bar is the original condition of your composition, product composition. So here we have the S bar 0.1025. So before the changes and after the changes. So in this case, when the S1 change to 0.5, the S2 change will calculate the product composition at 5 minutes. So in this case, so this is the before and after. So let's say this one is the before and this one is the after. Then definitely it will be increased to 0.2815. So this is after 5 minutes. So this is, let's say I put 0. Before the changes, I put 0. So this is the response before and after the changes. In this case, you can see that the maximum is 0.2815. Why? Because this one is based on the 5 minute. So it's not reaching the steady state yet. If the complete first order, it will start like this. So this is the black line represent the complete first order, where it is still increasing until it is maintained at the new steady state. So in this case, since the sketch requests only for the changes for product composition before and after, so we can use the calculated x equal to 0.2815 at 5 minutes. So this ultimately your response. And then lastly, draw the control loop configuration for the product composition. All right. So based on this, so this is your picture. All right. Okay. Now, based on this, we want to draw the control loop configuration. Of course, in this case, we have the CV, MV, and the DV. Before we come to the control loop configuration, it's better for us to understand what is our control variable, what is our manipulated and disturbance variable. In this case, the control variable will be our composition, product composition, the X. Because the W is constant, we assume the total flow rate in this case is constant, the total volume, so it's not affecting. So for this part, we have the X and then the MV. So for achieving the control variable, we can use either W1 or W2. Because it is much more easier to manipulate the flow rate compared to the composition. The flow rate, we can adjust the valve, how many flow rate that we want. So let's say we want 10 kilogram per hour, so it's a little bit easy to manipulate. If we try to manipulate the composition, 0.3 is a little bit difficult. So the normal practice in industry is to manipulate the flow rate rather than composition. That's why here the choice between the W1 and the W2. So for this part, we know that based on the given information, the W1 is equal to 10 and the W2 is equal to 800. W1 equal to 10 based on the given information. W1 equal to 10 and W2 equal to 800. So based on this, we already can decide the suitable manipulated variable for this case should be the W2 because it has a dominant effect due to the highest flow rate, 800 compared to the 10. Of course, 800 will give more effect compared to 10. So of course, in this case, we select the MV equal to W2. And of course, the W1 will become your disturbance. So this is the reason why we select the W2. Then for this part, okay, in this case, either you can start from the inside the line and then we have the CT, where the CT stands for the composition transmitter. C stands for the composition. The T is the transmitter. So CT is the composition transmitter. Then you have the dash line, you have the CC, composition controller. And then in this case, sorry, it's too big. Okay, I try to redraw it again. CT, CC. And then we have the valve over here at the W2. So this represents your control loop configuration for maintaining product composition. Any question?
Sir, let's say if we choose x2 as the manipulated variable, the disturbance variable will be x1 or blank.
Will be S1.
All right, so thank you.
Any other question? Okay, if there is no further question, then right now I would like to share with you one thing. Okay, in this case, if we take a look, for example, in this case, we have the derivation, and the derivation here, we obtain the first order transfer function. For example, in this case, the first order, the K1 is equal to W1 over W. So the W1 over W is equal to 0.013, K2, W2 over W equal to 0.9877, and the tau equal to rho V over W 2.22. Based on this, we can see that the value of K1, K2, and the tau has been obtained based on the value substitution, based on the given expression. For example, here we have the value of density, volume, and the flow rate. So we substitute the value, we get the value of the time constant. So this is normal practice. There are another way to obtain the K and the tau, which is from the graph. So here I would like you to share with you. Let's say in this case, Excel. So in this case, let's say I use some of the information before. For example, this one. So this is my K. (0.01). This is the magnitude, and this is the tau. So K equal to 0.01, 0.0123. 23, and the magnitude is equal to 0.2, and the tau equal to 2.22. So normally in this case, the equation, let's say I put y prime equal to k1 m1 1 minus exponent negative t over tau 1. So let's say here the y prime is equal to y bar equal to k1 m1 1 minus exponent negative t over tau 1. Where here, to make it simple, I put y bar equal to 0. So that reduce the y equal to k1 m1 1 minus exponent negative t over tau 1. Alright. So in this case, I can put the value inside. So it become y equal to 0.0123. M1 is the 0.2. 1 minus exponent negative t over 2.22. So based on this, when I supply the value of the time, then I can get the value of y. Y here I just define as my output. So here I put t and y. So let's say here I put 0 equal to 0.0123 multiply with the 0.2 multiply with the 1 minus exponent negative t over 2.22. Okay, so I have this one. Let's say I put it here. Alright. So this is the y value based on the calculation. So let me plot the graph. Alright. So according to this is my first order response. This is known as the first order response. So in this case, I just want to show you how to obtain K and the tau from the graph. Just for refresh. So here normally the K can be calculated using the following formula. K equal to delta output. The difference between the output divided by delta input. So this is the formula of obtaining the value of the K from the graph. So let's say in some time the K can be obtained directly based on the expression. You substitute the value of the variable, then you get the value of K. So in this case, there are another way to obtain the value of K, which is obtaining from the formula delta output over delta input. So since this one you have the delta, what is mean by delta? So the delta here is the difference between final value minus initial value. For example, delta output, the final value located at here, at the time, final time. So here the final time used is the 60. So this means 0.0025 minus the initial will be 0. So 0. And then here the delta input. So the delta input normally in this case referring to the magnitude. Magnitude of change. So the magnitude in this case is this. So this is normally is given to you because the magnitude is based on the step input. So normally this information is directly supplied to you. So you just use it. So the data input in this case will be 0.2. So that means here the K can be calculated. You get 0.0125. So this is how to obtain the K value. Or if we, in this case, why I use 0.245, or you can use 0.246 to get the clear answer. This is based on the what has been available. If you have the information of the y value 0.00246, you can use it. Or you can here, you can take the round off value. Both are acceptable. So in this case, since you have the 246, we can use that one, no problem. So 246. So of course you will get much correct answer. It depends what information if it is available. Sometimes in the test or final we just give you the graph, so it's little bit hard to get the interpolation correctly. So in this case, since the information is given, is available, then we can use it. So the value of the K is at 0.0123. And this is the formula for obtaining the K value. And lastly, the tau. The tau, this one is little bit fixed information. Tau normally at time when response reach 63.21%. So this is when you refer the textbook, they say refer to the third edition. It is in the page of 63, 62. When response reach 63.21%, the time taken is equivalent to time constant. So what is mean by 63.21%? Alright. So here you can see when the process start at 0, it reach 0.00246, the final value. So that means that one is what we call it 100%. So we need to find the value at 63.21%. So the 63.21, 0.6321 multiply with the 0.00246. So this equivalent to the 6321 multiply with the 0.00246. You get 0.00155. So this is the value when it is 63.21%. So 0.00155, if we take a look, it happened at here. Between 0.001461 and 0.001823. So this means if we try to do interpolation, we can find the exact answer. So for this part, we find out what is the value of 0.0155. So here, let's say 2.5, you get 0.0016. So we need to decrease a little bit. 0.616 is not 2.3, 2.2, 1547. So 2.21, 2.22. All right. So based on the interpolation, 2.22 provide the time taken to reach 0.00155. So the 0.00155 is located at here. So this is the point. So we take a look on the time. So this is the time represent 2.22. So this is your tau. So the tau is can be obtained from the graph based on the following rules. 63.21. This 63.21 is fixed, is standard for first order response. For first order. As long you have the first order response, you can use this following information. 63.21. So it's like that to find the K and the tau from the graph. So this is the added information to you. Any question?
Doktor,
Yeah.
nanti masa test akan guna Excel ke tak perlu?
Normally you don't need to use Excel.
Okey, doktor.
Since, however, you need to take note since we perform it online. Of course, you open your question in the laptop. So sometimes, if based on this, to do the interpolation quickly rather than using manual mode, it's much more easier to use Excel. So you are allowed to do that, no problem. Any question relating to the first order? So if there is no further question, then I think this is the end of our class. So I wish you best of luck for test. Please have a good look, have a good revision on the test. So with that, thank you very much again for your attention and cooperation, as well as for your response. Have a good day. So we end of our class today. And for your information, since we will have the test on Friday evening, then we will not have class on next Monday. So on Monday next week, Monday, which is 18 April, we don't have any class. I will see you again on next Wednesday, 20 of April. So with that, thank you again very much. Thank you again.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
All right, welcome.
Doctor.
Thank you, Doctor.
Thank you, Doctor.